Today we are pleased to have Uzi Pereg, one of our own. Uzi got his PhD degree from the Technion here with Yossi Steinberg, who is also at the audience. So it's nice to be, so it's going to be a friendly atmosphere, I think, Uzi, I think people you know. And he's now a postdoc at Munich, and he made significant, how would you say, development or change in his career path, and he moved into quantum information. His PhD was more in classical information theory, and we are delighted to have him tell us about his research during the year of Corona. Okay, so Uzi, the floor is yours, and go ahead.
Thank you, Yossi, for the introduction. This is a joint work with Christian Deppe and Holger Boche. In this work, we consider quantum broadcast communication with cooperation between the receivers. And through this setting, we provide an information theoretic perspective of quantum repeaters. I'll begin with the motivation. Attenuation in optical fibers poses a challenge for quantum communication since we cannot amplify as in classical systems. And this causes a severe restriction on the range of current applications of QKD, quantum key distribution, that aims to distribute a secret key between communicating parties, and then later this key can be used to establish information theoretic security using classical encryption such as the one-time pad. This challenge is also relevant for future implementation of the quantum internet and quantum networks in general. Now, Briegel et al. Proposed quantum repeaters as a potential solution where the distance is divided into smaller segments with quantum repeaters at the intermediate stations. Different implementations were proposed using quantum dots, trapped ions, and diamond Call centers. Now, straightforward amplification is not an option due to the no-cloning theorem. That is the principle that universal copying of quantum states stands in violation of quantum mechanics. So we cannot have this quantum Xerox machine that duplicates any quantum state. Now, here's the basic scheme of a quantum repeater has the following steps. First, we use quantum communication and entanglement distillation to prepare two pairs of entangled states. The first pair is between the sender and the repeater, and the second pair is between the repeater and the receiver. In the next step, the repeater performs the teleportation protocol to send the quantum state of the system P1 here onto B1, thus swapping the entanglement such that A and B1 are now entangled at twice the distance. In this protocol, it is assumed that there is no noise, and later we will talk about the effect of noise on this protocol. So I'll begin with a background on classical information theory, and later...
Can I ask you, Uzi, in the previous picture, so I understand the red curvy line, but what is the blue curvy line between P2 and B?
You need this to perform the teleportation protocol, right? Because teleportation requires an entangled pair.
So can you repeat what do I do? Can you repeat how the repeater works?
Both first of all, both P1 and P2 belong to the repeater. Okay.
Yes.
Now, at the beginning, there are two entangled states. Okay. Now, the repeater wants to send the state of P1 to the receiver. We want the receiver to be able to recover the state of P1.
Okay, so AP1 is the message.
AP1. No. The state of P1 is the message, and A is an external system that is entangled with the system that Alice, let's say teleportation with Alice and Bob, then here this is the state of Alice, and this is an external system that is entangled with Alice's state. Okay.
But at the end of the day, Alice wants to transmit a message to Bob through the repeater, right?
Okay. Here it's generating entanglement between Alice and the receiver. This is the end goal.
Okay.
We'll go back to the teleportation protocol later, and maybe I hope it will be clearer later, but if not, maybe you can ask me later again, okay?
Okay.
Okay. So let's begin with classical information theory. In the classical world, modern communication relies on error correction codes. Given a noisy channel, we know that error correction codes can reduce the probability of decoding error. And so this is the basic paradigm. Alice has a message that consists of k information bits, and then she has an encoding mapping. She maps the message into a sequence of n transmissions. Each transmission goes through the channel. The channel is modeled by this conditional probability function p of y given x. And then we have a random output sequence, y1 through n. Bob receives this output and uses his decoding mapping to estimate the message. He finds this estimate m hat, and the probability of error is the probability that m hat is not the same as m. So the performance of an error correction code is measured by the probability of error, but there is also a redundancy that is introduced in the code, and this redundancy can cause delays in the transmission. Therefore, we define the coding rate R as the fraction of k information bits per n transmissions. Codes can also be used to correct errors in memory, and then it is the ratio of logical bits per physical bit registers, or in quantum computation with fault tolerance, it is logical qubits per physical qubits, but I'll talk about quantum information later. Okay, so just to clarify the notation, I believe that many of you are familiar with the basic repetition, 3 repetition code. So then we have 2 possible messages, m equals 1 and m0 and 1. And then 0 is mapped into the sequence 0, 0, 0, and 1 is mapped to 1, 1, 1. Okay, so if the channel causes an error in the second bit, for example, then Bob receives 101, and then using a majority decision, he recovers the original message 1. Now, given a code with a specific probability of bit flip, one can calculate the probability of error of this code. And now the parameters of this code are k is the number of information bits, it's just 1, there's only 1 information bit of the message. Then the number of transmissions is n equals 3, and the rate is 1/3 of a bit per transmission. Okay. So of course, in general, the probability of error is some number between 0 and 1. But now Shannon introduced the notion of channel capacity. The capacity is the highest communication rate with probability of error that goes to 0, that tends to 0 as the number of transmissions, the block length, goes to infinity. And Shannon showed that the capacity has a simple formula. While the definition of the capacity is asymptotic, it has this limit of n going to infinity. The formula does not involve limits and does not include the block length. This is why it's called the single letter formula. Another viewpoint on this communication problem is through trading resources. So first, I'd like to define a resource inequality. If there is a protocol that uses a resource A to produce the resource B, then we write that A is greater than or equal to B. And we say that the protocol converts A into B. Or we also say that the protocol consumes the resource A and produces the resource B. This is especially relevant in quantum information, but I'll use it here to demonstrate. So let's look at those two resources. Here we have from C to C. This indicates a classical noiseless bit channel, or it's really the ability to send one classical bit without error. The second resource, P of y, is P of y given x. This is a single transmission over the noisy channel. So using channel coding, we obtain the following resource inequality. We use n transmissions over the noisy channel to produce or simulate k noiseless bit channel. Now, it's only noiseless asymptotically when the block length goes to infinity, and then we have a probability of error that goes to 0. And in general, k can also go to infinity. So if we divide both sides by n, then we get a finite coefficient here. We get the rate r, that is the fraction of information bits per transmission. I hope this is clear so far. If not, you're welcome to ask questions. Now, I mentioned the 3 repetition code, but for this code, the probability of error is positive. If we want...
Since I don't even pretend to know everything about information theory, so are you going to show us what is this Shannon single letter formula, or whatever you call it, or this will come later?
It will come later in, I think, 2 slides, or maybe 3. Okay. For now, I want to explain the idea of error correction. Okay, so for the basic repetition code, we have a positive probability of error. If instead we repeat the transmission of every bit n times, then the probability of error will go to 0, but the rate is 1 information bit per n transmission, so the rate will also go to 0. Therefore, the repetition code does not accomplish what Shannon promised, does not achieve positive rates. There are, however, other codes, such as Reed-Solomon codes and low-density parity check LDPC codes that are very common in practice and that achieve positive rates. Since they are also efficient, they are efficient constructions and encoding and decoding procedures for those codes. In addition, Arikan introduced in 2009 polar codes and showed that the rate approaches the Shannon capacity limit. So in current communication systems that we have today, we have near Shannon performance. So what in this talk, I will not talk about efficient constructions and specific coding schemes or algorithms. Instead, I will focus on what are the Shannon limits, what is the optimal rate of transmission. Okay, so for the classical channel, P of y given x, Shannon has shown that the capacity is given by the following formula. This answers your question, Yossi. So here we have a maximum of the mutual information between the random variables x and y, where we maximize over the input distribution, the distribution of x. Well, the channel is a constant, it's a given model. The mutual information is defined as the sum of the entropy of x plus the entropy of y minus the joint entropy. I haven't written here the formula for the classical Shannon entropy. Instead, I'll just talk about the intuition for now. So we think of about the entropy as a measure of uncertainty, the amount of uncertainty, how random is this x is, or how close its distribution to a uniform distribution. In this illustration, the entropy of x is the area of the left circle, and the entropy of y is that of the right circle. Okay, then the joint entropy, this is the overall uncertainty, so it is the area of the union of those sets, while the mutual information is the area of the intersection. So we think of the mutual information as an information measure for the correlation between the random variables x and y. If they are statistically independent, then the capacity is 0, because we are just receiving noise. Okay. Okay, I wanted to comment that we will see that for quantum systems, quantum entropies cannot necessarily be represented using this picture, because the joint entropy can actually be smaller than the entropy of one of the systems. Okay. Here, the joint entropy is always bigger, is larger than or equal to the entropy. And I'll try to explain why. So let's move on to quantum information theory, unless there are questions. So according to quantum mechanics, the wave function, that is a solution of the Schrödinger equation, gives a complete description of the physical state of an isolated system. So in quantum information, it is represented by a vector. A pure quantum state psi is a normalized vector in the Hilbert space, the vector space H of A. In particular, in 2 dimensions, for a quantum bit, which is known as a qubit, we can have the states 0, 1, or any superposition between 0 and 1, any convex combination, any linear combination of those wave functions 0 and 1. So if we think of real valued coefficients alpha and beta, then we can represent the quantum state as a vector that points onto the unit circle, while the classical states of a classical bit, 0 and 1, are represented by those vectors in red color. In general, though, the coefficients can have complex values, and then we can represent the quantum state in 3 dimensions using a Bloch sphere. Hope this is clear. If we have 2 systems, A and B, then the joint state is a vector in the product space, HA tensor HB. And then, for example, we can have the state I tensor J, and this means that the system A is in the state I, and the system B is in the state J. But again, we can also have any superposition of those product states. So this leads to the definition of entanglement. The systems A and B are said to be entangled if the joint state cannot be written as a product of 2 vectors. We cannot assign one vector to the system A and one vector to the system B. We need this joint description. For example, this is the maximally entangled state, phi. It is also called the state of an EPR pair, named after Einstein, Podolsky, and Rosen. And here we have a uniform superposition between 0, 0, plus, and 1, 1. Now, in order to include noise and classical correlation, we generalize the definition of a quantum state, and the state is, rho A is defined as an operator that has the properties of a density matrix. Although I will not go into those specific definitions, instead I'll just mention that by the spectral theorem, there exists a random variable x that has distribution p of x, such that the density matrix has the following eigen decomposition, where those probabilities are the eigenvalues, and the vectors psi x are the eigenvectors. Okay, here we have the adjoint, psi x dagger. So this is a matrix. We also need to define quantum measurement. Measurements are represented by a POVM. This is a short for positive operator valued measure. A POVM is defined as a set of positive semi-definite operators, lambda x, that sum up to the identity operator. And if we have this POVM that represents a measurement, then according to the Born rule, the probability to measure the outcome x is given by the trace of the measurement operator lambda x times the density matrix, times the quantum state of this system. So in general, we can have all sorts of measurements. in the special case where we choose lambda x to be projectors onto this eigenvector basis, then we get that the probability to measure x is exactly this p of x. But in general, we can measure in other bases and we can have other measurements. Okay, so let's talk about entropies. The von Neumann entropy or quantum entropy, h of a with respect to the state rho, is defined as minus the trace of rho log rho. The logarithm is applied to the eigenvalues, so we can also write the following expression for the quantum entropy. And those of you who have some knowledge on classical information theory recognize that this is exactly the classical Shannon entropy of the random variable x that I've shown in the previous slide. So the quantum entropy has similar properties to those of the classical entropy. We can also define the joint entropy of A and B by taking here the joint state. And now the conditional entropy of A given B is defined as the joint entropy minus the entropy of B. Now, in classical information theory, when we look at random variables, the conditional entropy always satisfies this relation. It's an identity, but it's not the definition. The definition is given in terms of actual conditioning, as we have in probability theory, and then we have average of entropies. Therefore, the properties of the conditional entropy are similar to those of the classical entropy without conditioning. Here, on the other hand, we will see very different properties, which will be demonstrated in the following example. Let's look at this maximally entangled state. So this is a pure state. It's a particular vector. And then it is represented by an operator that projects onto the direction of this vector. Okay? So it's a unit rank matrix. Therefore, the entropy of this joint state is equal to 0. And this reflects the view of quantum mechanics that the wave function or the pure state gives us complete information about the system. There's no uncertainty, and therefore the entropy is 0. However, if we look at just one system, if we look at Alice laboratory, say that those are electrons in Alice, one electron in Alice's lab and the other entangled electron is in Bob's land. Now, when Alice measures, whichever direction she measures, she will get spin up with probability half and spin down with probability half. So it's basically a coin toss for Alice. And mathematically, the reduced state of Alice is, we find it by taking the partial trace of the joint state. And then we get the following matrix. This matrix is already diagonal, so we can see the distribution of x is Bernoulli half. Therefore, the entropy of A, and by symmetry also the entropy of B, is equal to 1. And this makes sense. Alice has 1 bit of uncertainty. Okay. So we see that this view of quantum mechanics gives us a property that doesn't exist in classical information theory. Namely, the joint entropy is smaller than the entropy of each system separately. The joint system, the composite system, has less uncertainty than each system separately. And this implies that the conditional entropy is equal to -1. Okay, so for classical bits, the entropy is always between 0 and 1. But here for quantum bits, the conditional entropy can be between, is in the range of between -1 and 1. Then we define the quantum mutual information in an analogous manner as in classical information theory. And when we look at transmission of qubits, we will be interested in the coherent information from A to B, which is defined as minus the conditional entropy. So for classical systems, this cannot be positive. On the other hand, when we look at the maximally entangled state, we've seen that we have 1 bit of uncertainty for each system separately, but no uncertainty for the joint system. Therefore, the mutual information is equal to 2, while the coherent information is 1. Again, those are different properties compared to classical information theory, where when we look at classical random bits, the mutual information is also between 0 and 1. And we get the value 1 when we have maximal classical correlation, basically when those are uniform random bits that are equal to each other. So one way to interpret this property, this value, is that entanglement is a much stronger correlation compared to any classical correlation, compared to the maximal classical correlation. And those of you who have some background in quantum mechanics know that there is a lot more convincing evidence and experiments that really demonstrate that entanglement can lead to correlations that cannot be explained using classical descriptions, using classical probability theory. So we need this generalized framework of quantum information that leads to correlations that do not exist in classical probability theory. Okay, now I mentioned that the general quantum state, the noisy quantum state, can be written as a mixture of pure states of vectors. Another interpretation is that of a reduced state. There is always a reference system R that purifies the system A. This means that there exists this vector, this joint pure state of R and A. And when we take the partial trace of R, when we throw away the reference system, then we recover the original state. Now, we can make a similar observation on the evolution of quantum states as well. If we have a closed physical system, then according to the postulates of quantum mechanics, the evolution must be unitary. The state psi evolves to U times psi, where U is a unitary operator. In particular, this evolution is reversible. However, if we have a unitary transformation that leads to a composite system of B and E, Bob and Eve, and then when we throw away the environment, the system of Eve, then this evolution now is noisy. It is not reversible anymore. And this evolution is called a quantum channel. This is actually one of the representations of a quantum channel. It's called a Stin-spring dilation of the quantum channel. The formal definition is a completely positive trace-preserving map, but I will not go into those properties. Here, for us, a quantum channel is a mapping from the state of Alice to the state of Bob. This is what we need. So let's go back to trading resources. So we begin with those 3 noiseless resources. Again, we have from C to C. This is a noiseless bit channel, or the ability to send a bit without error. And then we also have from Q to Q, a noiseless qubit channel, or the ability to recover the state of 1 qubit without error. So those are dynamic resources, they go from Alice to Bob. And then we also add this static resource, phi. Phi is a pre-shared entangled qubit pair, or an EPR pair. And this is known in physics as a non-signaling correlation. We cannot use it to transmit information by itself. And we think of it as the quantum version of common randomness, of classical correlation. Now, a basic protocol in quantum information is the Teleportation Protocol. Here there is an illustration. The systems that are above the dashed line belong to Alice, and below the dashed line belong to Bob. So here, Alice and Bob share this entangled pair. Alice also has the state of a qubit. Then she performs some operations and measurements on the 2 qubits that she has, and she takes the measurement outcomes and transmit sends those 2 qubits to Bob. Bob performs some operations, and then he recovers the original state of Alice. Okay, so I believe that some of you are familiar with the teleportation protocol very well. I hope that, Yossi, with this you're more, this is more natural for you, I guess, right? No? Yes?
I'm very happy, yes.
Yes.
You could decorate Z with the power AB, which are the consequences of the measurement, but that's fine.
Exactly. So maybe some of you in the audience can tell me what would be the resource inequality for this protocol. In other words, what are the resources among those 3, C, Q, and phi? What are the resources that are consumed in the protocol, and what resource is produced in the protocol?
I would guess that the EPR pair is consumed, and what is produced is teleportation of this psi. Is this correct? I don't know. Did I pass the test?
Almost. We need an entangled pair, that's true, but Alice needs to be able to do what also? The dynamic.
Classical transmission.
Exactly. So what we consume in this protocol is 2 classical bit, noiseless bit channels or transmissions without error, plus in addition an entangled pair, and what we produce is the ability to recover the state of 1 qubit. Another basic protocol is the superdense coding protocol. Here again, Alice and Bob share an entangled pair, but now Alice has 2 classical bits. She performs some operations that are controlled by those bits. Then she sends a qubit to Bob, her share of the entangled pair. And Bob performs some operations and measurements onto those 2 qubits and recovers the classical bits of Alice. So what are the resources that are consumed and produced here?
Well, I would guess just the bell pair.
Sorry?
I would guess the bell pair is consumed. The EPR pair is consumed.
Okay. And what is the dynamic part that Alice needs to be able to do?
And then 2 qubits are transmitted.
1 qubit.
2 bits are transmitted.
This
1
is...
qubit, 2 bits are transmitted.
Yes, so this is the product, but Alice needs to be able to send her qubit to Bob.
I see. Okay, so I also need the quantum channel, yes. Mm-hmm.
Exactly. So we have 1 noiseless qubit channel plus an entangled pair are consumed in the protocol, and what we produce is 2 classical bit channels without error, without noise. Okay. Now, sometimes we're interested in looking at communication with entanglement assistance. This means that we assume that Alice and Bob have unlimited access to entangled pairs free of charge. Okay, it's like assuming common randomness in classical communication. And then we do not include the entangled pair in the trade-off. It doesn't really need to be free of charge. We can just say that we count the entanglement resources separately. In any case, it is not included in this inequality anymore. So this is the inequality for teleportation. If we repeat the protocol k over 2 times, then we obtain the following inequality. And now suppose that we have a quantum channel and we use channel coding. We use end transmissions over the quantum channel to simulate k noiseless bit channels, classical bits, okay? Then, together with the previous inequality, we produce k over 2 qubit channels without error. So what we deduce is that given a classical code that has the rate r, we can transmit qubits at the quantum rate, which we denote by q, that has half the value of the classical rate, assuming that we have entanglement assistance. Using the superdense coding protocol, we can make a similar argument in the opposite direction, So then we deduce that given entanglement assistance, the quantum capacity of this quantum channel with entanglement assistance has half the value of the classical capacity with entanglement assistance. Now, I'd like to make two comments. First of all, the units are not the same in this equation. Okay, it's only equation of the numbers, because on the right-hand side, we have classical bits per transmission, and on the left-hand side, we have quantum bits per transmission. The second comment is that if one looks at this and deduces that classical is worse than quantum, then this would be the wrong conclusion, okay? Because we look at the same quantum channel and we ask how many classical bits can be transmitted here, or we can ask how many qubits can be sent and recovered. Okay, and sending qubits is a much more demanding task, so it makes sense that we can send less qubits than classical bits. Okay, this is with assuming that we have entanglement assistance. To conclude,
I must say I was really confused by this last equality. Why isn't the two upstairs and not downstairs? Can you explain again the half? Why is it half and not two?
Here I have C, 2C are bigger than Q.
Yes.
Okay. I'm using short terms. Okay, so I can also write this on average as 1C is bigger than half Q. But this only has meaning when I talk about averages. So I multiply this by K, suppose that K is an even number. So you see that the number of classical bits that I use, classical bit channels that I use in teleportation is twice than the qubits that I get at the end of the protocol. Or half the number of qubits is the number of classical bits that I need in order to implement the protocol. Okay. And this means that if I can send K classical bits, then I can also send K over 2 qubits. Okay.
Yes.
Sending qubits is more difficult, because it's much more than just for Bob to recover the state. A quantum state is a much bigger requirement than for Bob to recover a qubit, a classical bit, right? And this is why the number of qubits that you can send over the same quantum channel, in both cases, I'm looking at the same I'm using the same quantum channel. The number of qubits is smaller. Qubits that I can send. Okay. If we're talking about a classical channel, I cannot send any qubits at all, right? I hope that this is clear now. Maybe. Okay, so here I conclude our discussion about quantum resources in communication. So when we code over a given quantum channel from Alice to Bob, we can use a classical code to simulate where we use n transmissions over the quantum channel to simulate k transmissions of classical bits without error. And then we have this rate R. We can also use a quantum code to simulate k prime transmissions of qubits as we have in teleportation. And then we have this quantum rate of information qubits per transmission. We also looked at codes with entanglement assistance, and then the protocol consumes a number of entangled pairs as well, and we can also count how many entangled pairs are we using in this code. So since we have different types of codes, there are also different categories for the capacity of a quantum channel, for the optimal coding rate of a given quantum channel. There is the classical capacity for the transmission of classical bits using the quantum channel. There is the quantum capacity for the transmission of quantum bits. And I've shown earlier the Shannon's capacity formula for a classical channel. We've seen that it is a simple single-letter formula. Unfortunately, in both of those cases, for a quantum channel, in general, we only have a multi-letter formula. We only have a formula that includes limits and that is more difficult to compute. Another interesting scenario that I've mentioned is with entanglement assistance. Then the capacity is strictly higher, unlike common randomness in classical communication. And another benefit is that we actually have a single letter computable formula for the entanglement assisted capacity. One can also consider a classical channel and ask what happens if Alice and Bob have access to entangled pairs. Then Charles Bennett, in their paper on the entanglement assisted capacity, they also showed that entanglement resources do not increase the capacity of a classical channel. A more surprising result was recently shown by Leditsky et al. For the multiple access channel. This is a network setting with 2 transmitters. They showed that entanglement resources that are shared between the transmitters can increase the achievable rates even when the channel is classical. And they show this by defining a channel in terms of a pseudo-telepathy game. A similar property also holds for the zero error capacity, but I will not talk about this. This is a very partial list of literatures that is relevant to this work. Here we extend the classical setting of a broadcast channel with cooperation that was first considered by Ron Dabora and Sergio Servetto, and they solved this for the degraded broadcast channel. It was later generalized by Yossi Steinberg to the general broadcast channel with degraded message set. And quantum networks have also been considered in different settings, including broadcast communication, relaying, environment assistance, repeater assistance. In a joint work with Roberto Ferrara and Matthew Bloch, we also recently considered key assistance for security settings and so on. Here, we consider quantum broadcast channels in 3 different settings of cooperation between the receivers. The first is entanglement resources that are shared between the receivers. The second, there's a question.
If you can go back to the previous slide, I don't understand something about the Mac.
This one or?
Yeah, this one, entangle. Okay, the entanglement is between the transmitters.
Yes.
Not a transmitter and receiver.
No.
Okay.
It's so when we say entanglement assistance, we usually mean between the transmitter and the receiver, but we can look at entanglement resources between 2 transmitters or between 2 receivers or between any 2 parties in a communication network.
Okay, so this I wouldn't, at least intuitively, I wouldn't say that this is surprising because it's between the transmitters.
Okay, there is some logic to it, but okay.
It's quite
given the line before.
If you take the entanglement between each transmitter and the receiver, but not between the transmitters themselves.
Okay.
Then the capacity is not increased, I think.
I think that some would say that it is surprising that, first of all, it's a classical channel. Everything is classical. The transmission, everything is classical, but you only add those entangled resources. And also, common randomness does not, in classical information theory, common randomness correlation doesn't.
Okay. I see.
Okay, so this is another.
Okay. I understand. Okay, that's okay. You're right.
But there is some sense to it. Okay, I mean, in one interpretation is that the transmitters are inserting entanglement into the channel, and also it's based on this game. The game is classical, but it has quantum strategies that outperform classical strategies. Okay, if I'll have time, maybe I'll show the game also. The second cooperation setting that we consider is classical conferencing. This means that receiver 1 can send classical bits to receiver 2. When we combine entanglement resources with classical conferencing, the receivers can use the teleportation protocol, so we get quantum conferencing, where receiver 1 can send the quantum state to receiver 2. We also obtain consequences on the primitive relay channel, where receiver 1 serves receiver 2 and does not have information of his own to decode. And we conclude with our observations on the trade-off between repeater-aided and repeater-less communication, as well as the bottleneck behavior of a quantum repeater. So let's look at broadcast channels. A quantum broadcast channel is a map from the state of Alice to the joint state of two receivers, Bob 1 and Bob 2. In our interpretation of a quantum repeater, Alice is the transmitter, Bob 1 is the repeater, and Bob 2 is the destination receiver. So let's look at entangled resources. Here, it's a network setting where Alice has two messages, classical messages, M0 and M1, and she maps those messages into the state, the quantum state of an input. The input consists of n systems. Okay, this notation, A super n, is for the tensor product of the Hilbert spaces of Alice. Those systems go into the channel. Then we have two pairs of systems, B1n and B2n. Bob 1 receives this channel output, combines it with his share of the entanglement resources, and then he performs a measurement to obtain his estimate of the messages. Similarly, Bob 2 measures his output and the entanglement resources. We look at degraded message sets. This means that M0 is a common message that both Bob 1 and Bob 2 need to decode, and M1 is a private message that only Bob 1 needs to decode. So this is the communication scheme. Alice chooses this common message that has K0 information bits for both users and a private message that has K1 information bits. She prepares this input state depending on the messages, whatever they are. And then Bob 1 and Bob 2 receive this joint output state and combine them with the entanglement resources, perform the measurements that are represented by the POVMs, lambda and gamma. So then the probability of error is given by this expression. Again, when we want to compute probabilities in quantum information, we take the trace of the measurement operators times the quantum state of the outputs. So it's a bit different from what we have in classical information theory with classical probability theory. Okay, we can also write this using a resource inequality, although it looks a bit complicated. We use n transmissions over the quantum broadcast channel and the number of entangled pairs that are shared between Bob 1 and Bob 2. And then we simulate K0 transmissions of a classical bit. Here we have C twice because we send it to Bob 1 and Bob 2, plus K1 classical bits that are only recovered by Bob 1. Since we have two types of messages, we also have two types of rates. We have the common rate R0 of common information bits and the private rate R1 of private information bits per transmission. Okay, and then we cannot assign one number, one capacity optimal rate. So we look at rate pairs R0 and R1 that are achievable with probability of error that tends to 0 as the number of transmissions go to infinity. And then we define the capacity region as the set of achievable rate pairs. Okay, so before I give our results on the capacity region, I'd like to comment on the BC Mac duality. In classical information theory, the duality between the broadcast channel that has one transmitter sending information to two receivers and the multiple access channel that has two transmitters sending information to one receiver, this duality is a useful property in the study of multiple input, multiple output channels in wireless communication. in fact, the capacity region of the Gaussian broadcast channel is the same as that of the Gaussian multiple access channel with a total power constraint when we switch the roles between the receivers and the transmitters. Now, as I mentioned, Leditsky et al. Showed that entanglement between transmitters can increase achievable rates even when the channel is classical. So now this raises the question, does the dual property hold? They show this using the magic square game. Can we use the magic square game to define a broadcast channel with this property? That is, can entanglement between receivers increase the achievable rates? The answer is no. We've shown that the capacity region is the same as if there are no entanglement resources. This first result that we have is actually a straightforward observation because the entangled resources have no correlations with the inputs or the outputs of the channel. Okay, so if there are no questions, maybe we can move to a less trivial setting. So this is a different setting. There are no entanglement resources. Instead, Bob 1 can send classical bits to Bob 2 at a constant rate C12. It's also called a bit pipe. So here we define this region, R sub CL, that is, CL stands for classical, of course, and it is given by this formula where we have auxiliary random variables, classical variables x0 and x1. We take the union over the probabilities and the collection of states. So in principle, this region is computable, but our capacity region, we've shown that the capacity region is given by the regularization of the region R sub CL. Regularization means that we need to compute the region for this product channel with tensor K, then normalize and take K to infinity. So this is a multi-letter formula that is not easy to compute. I should note that the single letter formula with K equals 1, this is an achievable rate. It's a lower bound, or an inner bound. But in general, this is not easy to compute, but unfortunately, it is an open problem to find a single letter formula even for the basic single user channel. So this is, I think, the biggest open problem in the most basic open problem in quantum information theory, in quantum Shannon theory and channel coding. Okay, nonetheless, for a Hadamard broadcast channel, we've shown this single letter formula. And
just to check that I know what you're talking about. So channel capacity for this broadcasting, for a broadcasting channel is not even a number. It's going to be a set, right?
Yes, yes. It's this is why we define this set.
Okay.
Okay. But even in the single user case, we still have a limit. Instead of this union to infinity, we have a limit, and then we have a maximum, and it's still difficult to compute even in the single user case. Okay.
It's a set in how many, is it embedded in some fixed number of dimensions? Like what, how many dimensions should I?
No, dimension is 2.
Yeah, it's 2 dimensions. You can draw it on an XY, okay, on a 2-dimension plane.
Great. Okay, thank
you. It is a pentagon. You can draw it and see that it's a pentagon. Okay, in general.
Thank you.
Sure, no problem. I think I'll skip the proof ideas because I don't really have time. Where I'll just say when we combine entanglement resources with classical conferencing, then the receivers can use the teleportation protocol, and the quantum conferencing rate is half the value of the classical conferencing rate. This is what confused you, Yossi, before, but we go back to it again. But as I mentioned, the units are not the same. I'd also like to note that when we look at transmissions of quantum systems or transmission of qubits, what we really mean is recover the state of a quantum system. Here we cannot have a common message system, M0, such that the state will be recovered by both Bob1 and Bob2. Because this would violate the no cloning theorem. This would mean that we can duplicate a general quantum state. So this is why we have two separate message systems, one for each receiver to decode. And quantum communication can also be extended to subspace transmission when we also preserve the entanglement with the environment of Alice. And we can also use quantum communication in order to generate entangled pairs, not just consume them. And then we can look at this multi-party entanglement problem that we have. The monogamy property of quantum entanglement says that Alice cannot have a single system and generate a maximally and generate entanglement such that this system will be maximally entangled with both Bob1 and Bob2 simultaneously. Instead, she can generate a GHZ state of this form, but then each pair of systems are not entangled. And she can also generate two entangled pairs, one with each receiver, by preparing this product state. So we've shown this achievable region. I think I don't have much time, right? How much time? Do I have any time left? Not really. I cannot hear you, Yossi, you're muted.
Since we started 5 minutes late, take 5 minutes more or so. Is this okay?
Okay. Yeah, this sounds good. So I have more time than I thought. We've found those achievable regions and also an upper bound. Those are regions that we cannot achieve something better than those rates. But I will skip the formulas. We also here there is also an example that illustrates the result. This example is a pure loss bosonic channel. The bosonic channel is a useful model in optical communication, so I think it is an interesting example. And it simply models a beam splitter. Okay, the input of the channel is the signal. It's a single mode. It's an annihilation operator, A hat, and those outputs go to Bob1 and Bob2. So here we have this environment mode that is in the vacuum state 0. I'm sorry that I'm not explaining it thoroughly. We also have the transmissivity eta that depends on the absorption length of the optical fiber and an input constraint on the mean photon number. So the capacity region is given in terms of thermal Gaussian states. We can see here a Gaussian mixture of states. And the entropy of a thermal state is given by the following formula that is denoted by G of n plus 1 log n plus 1 minus n log n, where n is the mean photon number. So it's different from what we have for Gaussian random variables. It also complicates the analysis in many cases. So we've shown that the following region, the set of those pairs Q1, Q2, can be achieved. We've shown this by plugging this joint state of the input and the auxiliary systems, where phi here is a two-mode squeeze state that purifies the thermal state. Okay, then we also obtained consequences on the quantum relay channel, primitive relay channel, where Bob1 does not decode any information, it just helps transmission of information to Bob2. So we obtained several bounds. We also introduced the entanglement formation lower bound, where achievability is based on channel simulation. Here we use results by Mario Berta and others. So here we use the relay to simulate a channel. This is the idea. So I'll conclude with our observations on quantum repeaters. As I mentioned, we view Alice Bob1 and Bob2 as the sender repeater and destination receiver. Since we also have a direct link from Alice to Bob2, our results show the trade-off between repeaterless communication directly to the receiver and relaying information through the repeater. And you can also see that in our formulas of the lower bound, we have a term to Bob2 that corresponds to repeaterless communication, and this minimum term that corresponds to quantum communication via the repeater. And here we see the bottleneck flow behavior due to the serial connection between the sender-repeater link from Alice to Bob1 and the repeater-receiver link from Bob1 to Bob2. The throughput is dictated by the smaller rate. It's like having a pipe that becomes smaller, and here we see this minimum. Although it's not a minimum between the capacities, it's a minimum that involves the coherent information. Thank you. I think my time is up, although it would be nice to add some comments, but I guess there's no time.
Thank you, Uzi. So now the floor is open to questions. Anybody has a question? Well, I have one. Can you show again the formula for the entropy in the bosonic channel, which was n+1 log n +1 minus something?
Sure. Yes.
Right.
Done here.
So this is a sufficiently complicated formula. So how does Gn behave as n is large? It goes logarithmically or like what?
Yes. Yes. Logarithmically. Yes.
Mm-hmm. I would expect that Gn would still grow with n, right? Is this a reasonable expectation?
Mm-hmm. Yes.
Of course, it
Yes.
goes with n, but
Yes.
I think it saturates, isn't it? Or not?
Yeah.
Does it?
It has this asymptote, which I don't remember this value, unfortunately.
Oh, it does not saturate.
Oh, it
Yeah.
grows actually. It grows.
It grows because you have the plus log n plus
You're
1.
right.
Yeah, I got confused with some capacity formulas of bosonic channels. Sorry. Yeah.
Yeah, actually it grows logarithmically with n.
Yeah.
Thank you. This is what I
It
thought.
grows logarithmically with n.
Yeah. It is concave, which is nice.
Yeah, it goes logarithmically. You just make here the arithmetics.
Yeah. It is
Because
what
you
I
have
find
n times log n plus 1 minus n log n. This saturates.
Right.
And then you have another term, log
Plus
n.
log 1 n plus 1.
Yeah.
And one more question. Can you compare again? You said that you can compare the capacity of a channel with and without repeaters. So which formula expresses this comparison between the capacity of channel with and without repeaters?
Okay, it's really the trade-off. In this formula, we have the sum of those terms. This is the coherent information. The input is A, but those systems, A1 bar and A2 bar, they are auxiliary systems. Okay, they are not part of the communication scheme. Okay, and we maximize over this joint state. And if you choose the state such that, okay, A cannot be maximally entangled with both of them, but with both of those systems, right, by the monogamy property of the entanglement. So if you choose this state such that A is, intuitively speaking at least, more entangled with A, then this term of direct transmission will be bigger, but the other term will be smaller. And it also goes in the other way. If you choose A to be more entangled with A1 bar, then the transmission, then you transmit more qubits through the repeater instead of directly. So this shows you the trade-off. And it depends on the channel model, which one is better. Okay, if the channel through the repeater is very noisy, then there's no point to use the repeater at all. But if the channel to directly, if the channel that goes through the receiver is better, then it can be beneficial to use the repeater, but it's not necessarily optimal to use only the repeater. Even if the channel through the repeater is better, it's not necessarily optimal to use only the repeater, because there's still noise.
So when you consider various noises, are the noises of the type that say bit flip or phase flip, or do you also allow losing qubits?
So the nice thing about this Shannon theoretic model and the definition of a quantum channel is that it's so general. It includes whatever you can think of, any quantum evolution and noiseless evolution, including measurement channels and state preparation, and all the channels that you can think of, the polarizing channel, error,
but including also losing qubits.
Erasure channels, bosonic channels. Okay, there is a subtle point with bosonic channels is that the dimensions is infinite, so we need to use discretization techniques that are quite similar to what we use in classical information theory, and then we can apply the results to bosonic channels as well.
Great. So, are there further questions, comments, insightful remarks, or? Okay, if there are none, yes, please go ahead.
I have a question. Hi, Uzi. Thank you for great. What I would like to continue the question that Yossi asked. When you say that that it doesn't matter what kind of noise I have. So suppose I actually lose some of the qubits along the way. Yes. Now, assume that my state is maximally entangled, for example, GDL state. And if I lose some of the qubits, my state becomes a lot less, or maybe not entangled at all. Mm-hmm. So how can I see, or how can I see that the protocol is taking into account losing the qubit and having my state being less entangled?
Okay, so first of all, maybe it's already clear, but I'll just want to say this. Maybe it will be good for other people in the audience that sorry. No. Yes, so no. Okay, what I wanted to show is this, yes, that losing qubits is included in the definition of a quantum channel, because you can think of it as, I mean, you lose qubits in favor of the environment, right? And so you can always purify, and therefore you can get, okay, it's not, it's like purification, but it's called a thin spring dilation or isometric extension. Anyway, so it is included in this definition of a quantum channel. And since it is a noisy channel, this is exactly why we use coding. Okay, we use a high dimension space. Okay, we have this dimension of a to the power of n, because we have n copies of this. Alice transmits n over n systems, and the dimension of okay, I'm speaking in a bit loose terms, but the dimension of the information is smaller than the dimension that you are transmitting through. So you have this redundancy, and this redundancy, this allows you to insert structure, and this structure allows you to correct errors. Okay. Okay. In quantum terms, it's a bit more or less clear what does it mean to correct errors, but when you talk about quantum states, instead of probability of error, you look at the norm distance, for example, between the states that Bob recovers and the original state. And then what we get is, using those error correction codes, we get that the error tends to 0 as the block length go to infinity. We don't get, Bob doesn't recover exactly the same state.
Yes, you have answered, I understand.
Okay, thanks. And maybe I can add this comment that I mentioned that in my opinion, the most basic big problem in quantum Shannon theory is the multi-letter formula. I put it at the end, sorry. Okay, so this is what we get in single user case. This formula is called the Holevo information. Okay, and according to the HSW theorem, that is named after Holevo, Schumacher, and Westmoreland, the classical capacity of a quantum channel is given by this multi-letter regularized formula. So this is not easy to compute, although Peter Shaw have shown that for a class of channels, it turns out into a single, it reduces into a single letter formula. And the question whether this reduces to a single letter formula in general, I mean, maybe when you look at this, maybe it does. It can be reduced. This maximum can be reduced to a single letter formula, and we do not see it. I think that the most popular book on quantum information and computation is the book by Nielsen and Chuang. And maybe I should say it more gently, but I'll say it anyway. There is a fundamental mistake in the book, in the chapter of quantum information theory. They say it is believed by many researchers, but has not been proved that allowing entangled signals does not increase the capacity. And the rest of the explanation leads to this conjecture that the Holevo information is additive. Exactly what it says here. And this conjecture lasted until 2009. Then Matthew Hastings showed that there are channels with super additivity, and then it was deduced that regularization is necessary. So the Holevo information is not necessarily a single letter capacity formula. It doesn't mean that it doesn't exist. It just means that we don't know it. Okay, and yes. However, Preskey referred to the current phase of quantum computation as the noisy intermediate scale quantum era, the NISQ area. And I believe what he wanted is to encourage researchers to develop algorithms that can be implemented on intermediate scale quantum computers, because today we only have quantum computers of intermediate scale. We don't have large scale quantum computers. So in this spirit, in one of my latest papers, I proposed the following model where we have an encoding constraint. We restrict the encoder to using states where there are sub-blocks of dimension D that are in a product state as we have here. And then this leads to the following capacity characterization, which can be viewed as finite regularization. But if this is a small number, we have small number of qubits that we can process at a time, then this is computable. And I brought this in the discussion because it's really an immediate consequences of the theorem, of one of the theorems in Nielsen and Chuang. So the section in this book turned out to be useful after all. I just wanted to clarify what we know and what we don't know about this big open problem. The general problem is still an open problem.
Right. Uzi, I wanted to thank you very much. You gave us much food for thought. And we need to digest all this wonderful information. And I want to thank you again.
Thank you. Thank you for having me.
Okay. תודה רבה.
תודה רבה. תודה רבה, עוזי.
תודה, עוזי.
תודה.
עוזי, להתראות.
להתראות.
תשלח את השקפים אם אתה יכול.
ודאי, כן.
ביי.
אני תרשום לעצמי.
ביי.
ברח לשום. ביי.
טוב, ההרצאה תהיה מוקלטת, אז אפשר יהיה...
לא, הקלטה זה דבר אחד, שקפים זה דבר שני.
אוקיי, מצוין.
ביי.
בסדר. ואני בטח אשמח לקבל איזה שיעור פרטי, אבל אני אטריד אותך בהזדמנות אחרת. תודה רבה. ביי.
תודה.
להתראות.
תודה, עוזי.
תודה רבה. נתראה בשמחות.